Yeah, so I'd first like to thank the organizers for the opportunity to come to this wonderful conference. So I've heard many times about this wonderful series of conferences and always hoped that one day I would get to go. So I'm very grateful to the organizers for inviting me this time. I've learned a lot so far. So this talk is a slightly amended title. Let's say Conjectures on Hitchin's hyperkähler metric on the moduli space of Higgs bundles, which right away I'll start writing M Higgs. And so this is kind of, I think there are some people here who've heard me talk about this before, and so for them it's kind of an update. So we'll say it's an update on the status of some relatively old now joint work with Gaiotto and Moore. The update consists in part of some new results in collaboration with David Dumas. So roughly speaking, the formulation of the conjecture more or less is in this joint work with Gaiotto and Moore, which was originally in physics. And the new results go some way toward establishing the conjectures, and that's this joint work with Dumas. So this is going to be about the moduli space of Higgs bundles. So let me first make a quick recollection about the moduli space of Higgs bundles. So I'll fix kind of now and forever. Maybe I can go a little higher. So I'll fix now and forever C, a compact Riemann surface. And G will be the group SUK. And now, so what's a Higgs bundle? So a Higgs bundle is a pair. A Higgs bundle, I'll just say Higgs bundle, I really mean G Higgs bundle over C. But I'll just summarize that as Higgs bundle. So a Higgs bundle is a pair, E and phi. So E is a holomorphic vector bundle. Holomorphic vector bundle of rank K over C. And phi is a kind of matrix, is a one-form valued endomorphism. So it's a global section, global holomorphic section of the endomorphism bundle, but tensor with the canonical bundle. So locally, it would literally be like a matrix of one forms, and that matrix is giving you the endomorphism of this bundle E. But concretely, that's what it is. It's this holomorphic object. And then I guess since I'm doing SUK, I have to say also that the determinant of this bundle should be trivialized. And the trace of phi should be 0. We could have talked about UK, and then we would do the same, but without these conditions. Okay. So that's what I mean by a Higgs bundle. That's what Hitchin meant by a Higgs bundle. And let's see. Oh, I see. You can't do two at once. Okay. Okay. So there's a moduli space of these. So there's a moduli space of. The moduli space I want is not the moduli space of all of them, but the moduli space of ones obeying some stability condition. So the moduli space of polystable Higgs bundles. That's what I'll call M Higgs. And so the way I'm presenting it to you, it comes to you sort of naturally as a complex space. It's a complex space and I'll call it the complex structure. I'll call it I1. So in a minute, I'm going to say this space is hyperkähler. It has a lot of complex structures. So that's why I'm slightly strangely calling this I1 rather than just I. Anyway, it has one complex structure that's kind of manifest from its description as a moduli space of vector bundles and one-form valued endomorphisms. Okay. So that's the space. That's the space we're talking about. And the main thing that I'm interested in is the hyperkähler metric on this space. So let me remind you what that is. So the construction of this metric. So the definition of this space, as I gave it to you so far, is somehow purely complex analytic thing, or even algebra geometric thing. But the construction of this metric, on the other hand, is really a gauge theory thing. It involves solving a PDE. So the big theorem is that if you're given a polystable Higgs bundle, E phi, there exists a so-called harmonic metric. So it's going to be a Hermitian metric in this bundle. So it comes to you just as a holomorphic thing, but now we're going to equip it with a Hermitian metric. Of course, it has lots of Hermitian metrics, but it has one best one, which is the harmonic metric. And the harmonic metric, so I'll call it H, it's the one for which the following equation is true. Let's see. So it's the one for which this equation is true. The curvature, F for curvature, of DH, the Chern connection, I'll write that in a second. So it doesn't say that the metric is flat, but it says the curvature is equal to the commutator of phi, of the Higgs field of phi and phi dagger. So this is like a two-form valued endomorphism. This is another two-form valued endomorphism. When I say adjoint, I have to tell you what I mean by adjoint. I mean the adjoint with respect to the Hermitian metric. So the metric appears here and also appears here. And the equation is that that's equal to 0. So that's Hitchin's equation. So DH here means the Chern connection. So if you have a holomorphic bundle with a Hermitian metric, there's just one connection compatible with both of those structures, and that's the one I mean. So that's a unitary connection. I don't think I need a metric on the canonical bundle. In fact, you don't need a metric even on the curve. So this equation is kind of conformally invariant. So, well, as it's written, I don't use a metric. Just in fact, I don't use a metric anywhere on the surface here. Yeah, that's right. But yes, I see what you mean. But nevertheless, you don't need a metric in the canonical bundle to write this.
He's just thinking of the adjoint as a 0, 1.
Yeah, that's right. You would need a metric. That's right. Thank you. You would need a metric to convert that back to a 1-0 form, but that's not what we're doing here. That's right. That's right. Thank you. So this is kind of a 1-0 form. This is a 0-1 form. You wedge them together and get a 1-1 form, and this is also a 1-1 form. So those are the things that you compare. Yeah. Thank you. Okay. So this is a big theorem. So this is a theorem of Hitchin and Simpson. The existence of harmonic metrics. Once you have the harmonic metric, that's sort of the key thing that you need to write down the metric on the moduli space. So let's see. So it's essentially going to be the an L2 metric. I'll just spell out slightly what I mean by that. Just to be sure. So a tangent vector tangent to the moduli space of Higgs bundles. So think of that as being like a little arc in the moduli space of Higgs bundles. It induces a variation. So think of it, it's a little arc of Higgs bundles, and all of them have these harmonic metrics. So you get a one-parameter family of, well, think of identifying, right. So if you have a little arc of Higgs bundles, all of them have unitary, all of them have these canonical harmonic metrics according to this theorem. So all of them you can think of as being Hermitian bundles. Suppose you just identify all of them with a single fixed Hermitian bundle. Then what you have is one Hermitian bundle with varying Higgs fields and connections in it. You take the L2 norm on those. So it induces a variation. I'll write it A dot and capital phi dot. So phi is phi minus phi dagger h. And I'm just writing this locally. So right, D is D plus A. So the variation of the connection is like a variation of the connection one form. So this is a pair of one form is valued in the unitary endomorphisms of E with its H. So if you have a tangent vector, you look at just the infinitesimal variation of this connection in this Higgs field. Now these are determined only up to gauge transformation because I made some choice of how I identified all my bundles with this fixed unitary one. So this thing is defined up to gauge transformation. And now what you do is now you take the L2 norm. So Hitchin's metric, the norm of this tangent vector is just going to be the L2 norm of that variation. So it's some integral over the curve. I take the norm of, take A dot squared and phi dot squared. Where here I choose the representative that's orthogonal to the gauge orbit. Or said otherwise, you choose the representative which minimizes this norm. So by gauge transformations, you make this as small as you can. That's the norm that you want. Okay. So that's Hitchin's metric on the moduli space of Higgs bundles. Let's see. So I'll go over here. Oh. These I just do by hand. Oh. Great. Okay, and now the cool fact about this metric is that it's actually hyperkähler. So from the way I'm presenting it here, if you kind of squint at it, you can see easily that it's kähler with respect to the complex structure that I told you. What's not so obvious from the way I'm presenting it is that it's actually kähler also with respect to a whole bunch of other complex structures. So it's actually a hyperkähler metric. Great. Okay, so now the question, what can we say about this metric? So what can we say explicitly about this metric? Okay. So I want to describe a kind of conjectural scheme for writing down this metric. So of course, this gauge theory description gives you, a definition of the metric, but I want a sort of explicit, sort of coordinate description of the metric. And so okay, in the next, 10 or 15 minutes, I'll tell you what's the conjecture that came from this joint work with Gaiotto and Moore. What's the conjecture about what this metric looks like? Okay. So now the eraser. And so somehow the key ingredient, in some sense, I guess there are two key ingredients, but both of them come from one object, which is the spectral curve. So let me take a few minutes to remind you or tell you what's the spectral curve. Spectral curves. Okay, so suppose I'm given a Higgs bundle. E phi. So that's a bundle with a one-form valued endomorphism. And so if I just look at the eigenvalues, so at every point of the curve, I could look at the eigenvalues of this endomorphism. So the eigenvalues of phi. And they sweep out a curve. They're not quite numbers because this is one-form valued. So rather than giving you a curve just in the trivial bundle, they give you a curve in the cotangent bundle of C. So the picture is, let's write the equation first. So sigma is points in the cotangent bundle such that they're eigenvalues. So what does that mean? It means the determinant of phi of z minus lambda is 0. So that's some subset inside of, it comes to you canonically sitting inside of the cotangent of C. So the picture is, if you like, here's C. Then at every point, I've got phi of z and I've got the eigenvalues of phi of z. And as I move, those make this curve, spectral curve. So here's sigma. And generically, they're all distinct, but they may cross each other at some points. And so this is a branched cover. So this is a k to 1 branched cover. And because phi is holomorphic, it's holomorphic. So this is, yes, that's what it is. Okay, so anytime you have a Higgs bundle, you get canonically this k to 1 branch cover of C. And somehow, one of the, how can I say? If you take only one thing from this talk, if you understand only one thing that I say, that thing should be that the spectral curve is somehow much, much more powerful even than I thought. And I think we all already thought that the spectral curve is a pretty important thing. But it's actually even more important than I thought, in the sense that you would have thought, at least I would have thought, that solving this equation doesn't have so much to do directly with the spectral curve, right? Because there's no sense in which the solution of this equation is diagonal with respect to the spaces. It's not like the eigenspaces are orthogonal or anything like that. Nevertheless, it turns out that, well, if these conjectures are correct, everything you need to know about the metric comes from the spectral curve in a pretty strong sense. So I'll try to explain what I mean by that. And to be concrete, to be particularly concrete, let's talk about the case that k is 2. So then what is this equation like, right? So then this equation just becomes, it just says lambda squared minus phi 2 is 0. Where phi 2 is a holomorphic quadratic differential. It's 1/2 the trace of phi squared. So that's a holomorphic quadratic differential. So in that case, the data of the spectral curve is the same as the data of this holomorphic quadratic differential. So another way of saying what I said is that this holomorphic quadratic differential is super important. And you can kind of do everything in terms of it. Okay. So let me draw a picture of what this moduli space looks like. I mean, I think many people here know this picture very well, but maybe not everybody. So I'll just draw this picture. The moduli space of Higgs bundles is a complex integrable system, meaning that it's naturally fibered in the complex structure I've been mainly discussing. It's naturally fibered over a kind of half-dimensional base. And the generic fiber looks like a torus. Well, sorry, not looks like a torus. The generic fiber is a torus, an abelian variety, compact complex torus. And then there are some singular fibers. There's some complex codimension 1 discriminant locus. So here's the discriminant locus. I'll call that delta. So here's a point in B minus delta. And what is this map? So this B, think of as being the space of possible spectral curves. So when you move this way, you're varying the spectral curve. So this direction is like deformations of the spectral curve. And this way, moving in the fiber is some deformation which leaves the spectral curve fixed. In fact, you can think of that as varying a line bundle over the spectral curve. But anyway, some other deformations. Okay. So here's the kind of, complex analytic picture of what this moduli space looks like. And my description of the metric is going to be sort of naturally understood in terms of this picture. And it has a lot in common actually with the description of collapsing metrics on K3 that was in the last talk yesterday. So this is going to be a kind of parallel picture, except that instead of a K3 surface, it's moduli space of Higgs bundles. So that's easier in one way and harder in another. I guess it's easier somehow because it's non-compact. So for K3, the base of this fibration would be a 2 torus. Here it's an affine space. I drew it like complex, it's literally an affine space. Like for K equals 2, it's literally the space of quadratic differentials. On the other hand, you could say this case is harder because it's higher dimensional. It's not typically complex. Well, in fact, yeah, in the situation I'm describing, the base is never complex one-dimensional. The smallest it could be is 3. So it's always a kind of higher dimensional analog of that K3 picture. Okay. Okay, so now I want to start telling you what the conjecture about the metric is. And so let me start with the semi-flat metric. Okay, so concretely, to give you metric, what do I have to do, right? I already told you it's hyperkähler, and I told you one of the complex structures, what the space looks like in one of the complex structures. So to give you the metric, I have to give you the Kähler form. For example, one way to give you the metric would be to give you the Kähler form in that structure. So let's do that. So to describe the metric, let's do it by giving the Kähler form omega 1, so corresponding to the complex structure I1. And I'll give you kind of a first cut at it. So the first approximation. So this is not supposed to be the exact metric, but on the other hand, it is somehow surprisingly close, according to these conjectures, so here it is. It's del bar of some explicit Kähler potential, which I'll call KSF. This part is going to give the metric kind of in the spectral curve directions along the base. And then there's a fiber part, which I'll just write omega fiber. So this KSF, so this is something completely built from the spectral curve. In fact, what it is just the L2 norm of a tautological form on the spectral curve. So almost the most obvious thing you could do. This spectral curve, because it sits inside of the cotangent bundle, it comes with a canonical form, which is the Liouville form. So lambda is the Liouville form, right? A holomorphic 1 form on the cotangent of C. Right, it's the one which in local coordinates you would write P dq, that one. So we take that guy, just restrict it to the spectral curve, and then just take the L2 norm of that. That gives you kind of the interesting part of the Kähler potential. So there's that plus this omega fiber. So omega fiber, I don't want to introduce the necessary coordinates, but let's just say this is a translation invariant 2 form along the fiber, and it's built from all you use to build this 2 form is the intersection pairing on the homology. So the point is both of these things, okay, first one is that both of these things just come from the spectral curve in a kind of simple way. Okay, so what are the properties of this metric? Sorry, I think I would have got this by now. So this metric, as I wrote it, is absolutely perfectly good hyperkähler metric. On the other hand, the way I wrote it is, you can see sort of almost immediately that it's kind of translation invariant on the torus fibers. So this is a metric, that's why it's called semi-flat. It's in particular flat on the torus fibers. But even more than that, it's actually translation invariant on the torus fibers. So let's see, just write it here. So this omega 1 SF, if I look at the corresponding metric, GSF, so it's translation invariant in the torus directions. And hyperkähler. Now, but because it's translation invariant, sorry, I should have said and didn't say, that formula, of course, only makes sense when the spectral curve is smooth. So I wrote the integral of lambda wedge lambda bar. That formula only makes sense when the spectral curve is smooth. This discriminant locus is exactly the locus where the spectral curve is not smooth. And so the formula, as I wrote it, doesn't obviously extend over this locus. And that's the problem with it. In fact, if you think about it for a minute, you see that it kind of can't extend over this locus, because what does it look like? So let's write the statement. It doesn't extend over the discriminant locus. And sort of morally, the reason why not, if you want a kind of geometric reason why not, is that you know what's supposed to happen at the discriminant locus. At least in the sort of simplest, most generic kind of discriminant point, what has to happen is that in one direction of this torus, you develop this kind of node picture. And it's literally geometrically this picture, in the sense that if you come very close to this place, what you see is a thing that's kind of lumpy like this. It's bigger in some places, and then it has a very short cycle someplace that's going to 0 as you go to here. So the actual smooth Hitchin's hyperkähler metric is supposed to look like this. It's supposed to be pinched off at a specific point. Now the metric I just told you, it has the property of being absolutely translationally invariant along the torus fibers. So this can't be the right one to extend, because this one doesn't know that it has to pinch off in a particular place. But the claim is, the conjecture is that the actual metric nevertheless is very close to this one, in a sense I'll make precise in a second, when you go far away from the discriminant locus. When you go far away from the discriminant locus, the metric is supposed to be kind of exponentially close to this translationally invariant one. Yeah, so that's maybe the first form. I'm going to give sort of progressively stronger versions of this conjecture. And I guess this is sort of the weakest version of the conjecture, is that as we follow, let's just say it like this, as we follow a ray to infinity in the base, omitting the discriminant locus. So as we follow, say, this ray out to infinity in the base, the metric minus the semi-flat metric goes to 0. Yeah, and so this is a lot like Gross and Wilson's picture of a collapsing family of K3 surfaces. Here it sounds different because we're not talking about collapsing, instead we're talking about going to infinity, but by sort of conformal rescaling you can see that those things are more or less the same. So this is really like Gross and Wilson's picture, just as in Adam's talk. Okay, so that's sort of the first weakest version of the conjecture, is that the metric goes to this semi-flat metric. Now, suppose I want to describe more concretely the kind of correction you have to add to get away from the semi-flat metric. So then we're going to need one new ingredient. And the surprising part for me is that that new ingredient is also in terms, in a sense, but I think in a meaningful sense, is also in terms of the spectral curve. So what I would have naively thought is that this is where the spectral curve involvement ends. The rest of the problem is really non-abelian and doesn't have to do with the spectral curve. But in fact, if the conjecture is correct, even the exact metric really has to do with the spectral curve. So, okay, so what's the extra ingredient? So the extra ingredient is some integer invariance, which I'll call Donaldson-Thomas invariance. In some world they actually are Donaldson-Thomas invariants, but for now let's just think of them as some bunch of integers that have to go into the construction of the metric. Okay, so what did I say? So the true metric G is not equal to GSF. We want to write the true metric. So to write the conjectural G, we're going to use one more ingredient. So it'll be some numbers that I'll write dt of gamma. They're integers, where gamma is a homology class, a one-cycle class in the spectral curve. And now what I'm going to say now is absolutely not a theorem, but I think it's a good heuristic for what these integers are, a good way of thinking about them. The heuristic is like this. This integer dt of gamma, well, it's an integer, it's counting something. And what it's a count of is, it's a count of special Lagrangian two chains inside of the cotangent bundle. It's going to be two chains in the cotangent bundle whose boundary is on the spectral curve. So D inside of the cotangent bundle whose boundary lies on the spectral curve. So the picture is like this. Here's the base curve. Here's the covering sigma. And it, well, it's convenient to picture them like this. So here's the covering sigma. Here are some branch points. And now let me draw a special Lagrangian disk inside of the cotangent bundle whose boundary lies on the spectral curve. I'm kind of cheating you in various ways. I'm pretending that the cotangent bundle of the curve is hyperkähler so that it makes sense to talk about special Lagrangian. Okay, it's not true, but it's true in some neighborhood of the zero section. So you should imagine that all this is kind of pressed down near the zero section. But that's why this is a heuristic. I still think it's somehow a useful enough heuristic to talk about. And what's gamma? So gamma is the homology class of the boundary. So here's the boundary of that curve. That's some one cycle. The boundary of D is some one cycle on the spectral curve. That's gamma. So the homology class of boundary of D is gamma. So the integer dt of gamma is somehow counting all the two chains whose boundary is gamma inside of the cotangent bundle. And so that's the sense in which this is also geometry of the spectral curve. It's just slightly fancier geometry. It's geometry now of things. It's this kind of geometric counting problem still involving the spectral curve. And this is going to be the only extra ingredient that we need. So that's the sense in which the spectral curve is supposed to determine everything. It's sort of the classical geometry plus these instantons that's supposed to determine everything. But now what I just said is not quite a definition, and I want to tell you as precisely as I can this conjecture in some example. So let me say how we might actually define this invariant in some example. This invariant is what I usually call omega of gamma, by the way. I'm just calling it dt because it's somehow one less thing to remember. You remember that that's Donaldson-Thomas. But if someone's heard this before and thinks I'm changing it, no, this is the thing that used to be called omega of gamma. Okay, so to actually define this invariant, to define this number, to really define it, what we use, instead of trying to solve this problem of special Lagrangians and some hyperkähler metric that we don't know, you use a kind of tropical version of it. And let me spell this out only when k is 2. That's the simplest case. So then it's the picture just like I drew above. So here's our base curve here. Here's our spectral cover. And then think of your little disk as being just foliated by little vertical lines inside of the cotangent bundle, straight lines in the fibers of the cotangent bundle. Then this thing is lying over some trajectory in the base curve C. So now this is going to be just a problem of trajectories on this Riemann surface. And the trajectory has to obey an equation which is supposed to be the analog of the special Lagrangian condition here. And the condition is Well, okay, so it's going to be a thing of finite length, but the equation that it obeys is that it should be a geodesic. Geodesics in what metric? Well, remember, the data of this spectral curve in this case was the same as the data of just a quadratic differential, holomorphic quadratic differential. So that induces a kind of singular flat metric on the surface. And all we do is we count the finite length geodesics in that metric. That's what gives us this omega of gamma. Okay, so to be just very slightly more precise, if I have a finite length geodesic like this, it lifts to some cycle gamma up here, and this one will contribute +1 to my count. So I count it literally in the most obvious way. It's just isolated object counts 1. But there's actually a trickier thing that you can have. You can have an annulus swept out by closed loops. So if you have closed geodesics, they actually come in a one parameter family, and that whole one parameter family will contribute -2 to this invariant. Okay, so now in this simple case, in the case of SU2, now I've completely told you the definition of this invariant. You count these things with +1 and these things with -2. Okay. So those are the numbers that are going to enter into this conjectural picture of the metric. Okay. So now I can say a little sharper what the conjectural picture of the metric is supposed to be. Sorry, by the end I will master this. Okay. Yeah. Wait, no, sorry, yeah. So in that case, so imagine you just have one finite length, one closed geodesic on the surface in this flat metric. Then, if you think about what the trajectories, what the geodesics look like nearby that one, you can see that it's not isolated. It's sitting in a one parameter family of them. So there's like an annulus that's just swept out by these closed geodesics. Now then you ask, what happens to that annulus? It has to end somewhere, right? It doesn't fill up the whole surface. So how does it end? And the way that it ends is by bumping into singularities of the metric, which are the branch points. So that's what I pictured there. You see two branch points on the two ends of this annulus. So the kind of boundaries of the annulus are trajectories that exit that branch point and return to the same branch point. That's how that annulus kind of ends. So that whole annulus contributes -2 to one of these dt of gammas. And this, I should say, this is a very classically studied thing by people in type Miller theory know these very well, these geodesics and closed geodesics and saddle connections. And they prove a lot of marvelous theorems about them. Okay, which I don't know that much about, so I won't try to say more. Okay, so let me try to say a little sharper now, what's the conjecture about the metric? So
this definition makes sense even when you have multiplicity for the zeros.
Oh, no. Yeah, I mean, you can. So, yeah, sorry. So I should have said, oh, no, in a sense I did say. So I'm always working away from the discriminant locus. The discriminant, in the language of this quadratic differential, the discriminant locus is the locus where the quadratic differential develops a multiple zero. So no, in everything I'm saying away from that locus. It's very interesting to try to extend this conjecture over the locus, over the discriminant locus where you have multiple zeros. But let me not try to talk about that. Yeah, so here I'm always assuming that all the zeros are simple, which is what it means to be off the discriminant locus. Okay, okay, sharper conjectures. Okay, so conjecture 2, and again, this is more or less contained in this old work with Gaiotto and more. So again, let's say as we follow a ray to infinity in the base, the difference G minus GSF, so before I just said it goes to 0, but now let me say a little sharper how it goes to 0. It goes to 0 like the difference is, bounded by some constant times e to the minus 4m. So m is, so first of all, it's exponential, but exponential in what constant? So if the group is SU2, m means the length of the shortest finite geodesic. And by length, I mean the length in this flat metric, phi2 length. So as you go to infinity, going to infinity along an array literally means you just uniformly scale up this flat metric. So the length of the shortest finite geodesic, whatever it is getting longer and longer as you go off to infinity. And the statement is that the convergence is exponential in that parameter, e to the minus 4 times the length of the shortest finite geodesic.
Is it closed geodesic or also this open geodesic?
Oh no, it's usually an open one. I think maybe it's always an open. No, I'm really thinking of, so finite length means, because the metric is singular, the geodesics have to stop at the branch points. So that's what I mean by a finite length geodesic. That's why I'm calling that a finite length geodesic. So I think it might be always one of these saddle connections, one of these guys that counts +1. And then, now here there's actually a theorem. So that's the new thing. I think you'll hear more about this in the talk of Jan Swoboda, and maybe also the talk of Laura Fredrickson. So I won't try to say much about the kind of methods that are used in proving the theorem, but let me just say what the theorem is. But I mean, in proving this theorem, we benefited a lot from discussions with Fredrickson, Swoboda, and Matteo, Weiss, and Witt. The theorem is so it's proved with David Dumas. So this is just for SU2. So the conjecture is for all SUN, but the theorem is only for SU2. And what's worse, it's not for the whole metric, it's for the restriction of the metric to one special section of the Hitchin fibration. So the restriction of G to this half-dimensional slice called the Hitchin section. The Hitchin section is the case where the Higgs bundle is k to the half plus k to the minus a half. And the Higgs field is of the form 0, 1, quadratic differential, and 0. So this gives you one Higgs bundle for every quadratic differential, so that's a section. Anyway, if we just restrict to that section, we can prove this theorem. And the theorem is G minus G semi-flat decays as order e to the minus 2m. And unfortunately, the 2 is not a mistake. So we were excited that we got it exponential, because there was this question, is it exponential or not? So at least the conjecture is somewhat vindicated, but on the other hand, we missed this factor of 2. Okay. But at least this is actually a theorem. So now, in formulating this part of the story, so this is still kind of the asymptotic story, and of course in formulating this, I didn't use those integers dt of gamma. All I used was the length of the shortest geodesic. And I didn't give you a conjecture for the exact metric, I only gave you some asymptotic statement. Okay, so the last thing I want to do is to tell you kind of what the whole maximal conjecture is supposed to be. But again, I'll just restrict it to the Hitchin section. But I'll tell you what's the maximal conjecture on the Hitchin section. And I'll give you a little bit of evidence for that version. Okay, so here's the kind of maximal conjecture. So, I have to introduce a tiny bit of notation. Not too much, I think. So we're going to have to, let's use a basis for the homology of the spectral curve. So again, everything's in terms of the spectral curve. That's the key gadget. So now the conjecture is that the restriction of G to the Hitchin section has Kähler form. So before I wrote this semi-flat expression for the Kähler form, now I'm going to try to write the exact Kähler form. So it comes in this shape. It's the real part. It's going to be the real part of something holomorphic, actually. It comes somehow from the twistor space picture of the space. So we'll sum over I and j. And what you really do is you write down kind of holomorphic Darboux coordinates. So dx gamma I, dx gamma j. These coordinates are going to be functions of a twistor parameter, and we'll just evaluate them at twistor parameter equals 1. So I have to tell you what are these functions x gamma. That's kind of somehow the key thing. And what they are, so these are some functions on the Hitchin moduli space. And I'll tell them to you. Skew symmetric. Yes, skew symmetric. Oh, sorry, this is obviously, sorry, obviously I messed up the, yeah, how do I fix it? Oh no, it's fine, it's fine. Oh yeah, so when I exchange I and, no, but that's fine, right? Had it not been like that, I mean, yeah, this is a two-form. I mean, think of the case where this is just like writing dx wedge dy minus dy wedge dx. It's just which is the same as 2 times dx wedge dy. So the prefactor is skew symmetric, so there's a minus, and also the wedge product is skew symmetric. So no, it's fine. The whole thing is an honest 2 form. Yeah. So the key thing is to tell you about these functions. So these functions x gamma I, so that's a map from C star to C. We're evaluating it at 1, but it comes to you as a function from C star to C. That's kind of the twistor picture of this space. So they have to obey this integral equation. Let me write the equation. Oh yeah, sorry, thank you. C star cross M Higgs. 10 minutes, okay. Great. Yeah, that's important enough that I should. C star cross M Higgs. But that 1 there is the C star parameter that I wrote explicitly. So they have to obey an equation. So let's write the equation.
Is this just the homology or the
Yeah, you're right, because I said SUN, right? So you're right, thank you. So it should really be a basis just for the odd part. Yeah. And in general, it should be kind of the prim part. So I'm trying to say the conjecture even for SUN. So yeah, so you're right. It's not the whole homology, but it's the prim part of the homology. Sorry, thank you. So here's the. Yeah, so in other words, there's some, I should have said there's a restriction to some sublattice inside of H1 of sigma z, the part that's killed by the projection to the base. So here's the equation that x gamma has to obey. It's an integral equation. But again, the key thing is that this equation, it looks complicated, but it's formulated just in terms of data of the spectral curve. So it uses these integers, dt of mu. It uses the intersection pairing, and it uses some numbers z gamma. Let me say right away what z gamma is. Z gamma is just the period of the holomorphic 1 form. So we have this holomorphic 1 form. So far we didn't explicitly use its periods. These are just some complex numbers. So those complex numbers enter here and here. Now this is going to be an integral. The integral is over some ray in the complex plane. whose position is determined by z again. And just some explicit integral operator. So d zeta prime over zeta prime plus zeta over zeta prime minus zeta log of 1 plus or minus e to the x mu of zeta prime. There's a kind of tricky sign that enters here. Let me not try to explain that sign. But it's 1 plus or minus. Okay. So let's say a word about this. So this is really an integral equation in the sense that the functions x gamma of zeta appear both on the right side and left side of this equation. So this is not a formula. This is an equation which you can try to solve. But the way you can try to solve it in practice is to make some initial guess. You make an initial guess that the function is just given by this. That these terms. So this part here, if you just took this part, you would get the semi-flat metric on the nose. The initial guess is that the metric is close to the semi-flat metric. So what you do, you guess that it's this, then you plug that into this integral operator, you repeat, and you hope that the thing converges. And the conjecture is that it does converge. It converges to give you some functions, and then you evaluate those functions at 1, compute this Kähler form, and that gives you the Hitchin's metric. So.
And is there again a minus sign on H1?
Yeah. Sorry. Yes. The same question. Yeah. So let's. Yeah. Everywhere it should be this sublattice. Yeah. Okay. So there's the conjecture. Rather than trying to tell you where the conjecture comes from, let me show you some evidence for the conjecture. So this is far from being proved. But there is newly some kind of numerical evidence that the conjecture is true. By which I mean you actually calculate Hitchin's metric, you solve these integral equations, and you check that the metrics are the same. In other words, that the gauge theory computation is equal to the computation with this integral equation. So let's see if this is going to work. Okay. Oh, you can't see anything. Has the projector turned itself off? It was turned on early. I think it must have switched itself off during the presentation. Yeah, I want to turn it. Yeah. My laptop is connected. Yes. Okay, but while it's coming up, let me tell you what we're going to check. So this is going to be a little bit of a cheat because I'm going to show you an example which is not exactly an example of what I claim. So it's an example of a case of Higgs bundles with a singularity on CP1. That sounds like it would be harder, but it's actually much easier. So the numerical tests are Higgs bundles. So it'll be SU2. Group is SU2. It'll be Higgs bundles on CP1 with a so-called irregular singularity at z equals infinity. But there's a theory due to Biquard, Bolch, and Mochizuki where I think it's now agreed that moduli spaces of Higgs bundles with irregular singularity also have hyperkähler metrics. So in short, the theory is supposed to be completely parallel to what I told you, but just easier to study. In particular, here you can get an actual one-dimensional example. I told you that there's no example where the base is one-dimensional. And that's true if you restrict to compact curves. But if you do these things with irregular singularity, you can get a simpler thing. And so let's take the very special case where the bundle is O of, it'll be a kind of parabolic, so there's some parabolic structure in infinity. So the bundle is kind of O of 3/4 plus O of minus 3/4. So I mean a bundle of parabolic degree, this parabolic degree. And the Higgs field will be this explicit Higgs field, 0, 1, z cubed plus lambda z plus u. So it depends on two parameters, lambda and u, 0. And the idea is that lambda you hold fixed. That's one of the parameters defining the moduli space. And u is allowed to vary. So U is like the coordinate on the Hitchin section. So it's literally one-dimensional. So we literally have a one-dimensional complex space parameterized by U. We're going to make a little variation of U, and we're going to compute the metric. Okay. And so, yeah, so the formula is supposed to be exactly the same. The spectral curves, the spectral curve is just literally, it's literally a cubic curve. Y squared equals this. And so they're nice genus 1 curves that you can study. You can compute the periods. And the cool thing in this case is that, so here it's literally a cubic polynomial. It just has 3 zeros. So the picture is the spectral curve is like a cover of the plane branched at these 3 points. And there'll just be 2 finite length geodesics. On a compact curve, there's always infinitely many, so these sums I'm writing are infinite and you have to worry a lot. Here, there's just going to be 2 of them. And so we have some chance of actually doing this thing numerically. Okay, so I hope you can see this a little bit. So we're going to calculate with the parameter lambda equals 0.4 and c equals 1. Oh, sorry, c is what I called u here. Let's call it c. And we're going to compute GCC bar, right? The metric element GCC bar. Okay. And so this is part of the joint work with David Dumas. So the computer program, so the first thing it does is it does literally Hitchin's definition, meaning that it has to actually solve Hitchin's equations in the plane. But that's something that you can do. In this specific case, it actually reduces to just a scalar PDE. It's just Laplace equation with some explicit, I mean, it's not literally a Laplace equation, but it's an elliptic equation. The highest order part is the Laplace. So now it's just solving that PDE. And then it's going to solve the linearization of the PDE to do the tangent vector. And it'll compute the norm from that. Okay, so now it's going to do the, all right, so yeah, now it's doing the linearization. I forget why, but it has to do linearization twice. Oh yeah, because there's 2 equations. Okay, oh good. Now it's doing the integral equations. Okay. So there's, I don't know if you can see it, there's the metric element. So computed by the 2 methods. So it's 2.0376, and then the next digit disagrees, so it's 7 or 8. But this we think, I mean, there's plenty of sources of numerical error in this computation. A priori, they didn't have to agree at all. So we regard this kind of thing as pretty good evidence that this conjecture is somehow on the right track. So it's still far from being proved, but at least now there's some actual evidence that it should be true. Okay, I think I'll stop. So, thank you.